yesterday we did RC circuits, correct? Today I want to do RL circuits. It is remarkably similar to RC circuits. So a lot of stuff I will be just skimming over and talking to you about the main things. Okay, so let's do RL circuits. So the picture of an RL circuit will be similar to the picture that we had for the RC circuit, where there will be a switch AB connected to a resistance, connected to an inductor, connected here with an EMF source here. And when the switch is at position A, the battery is in the circuit. If the switch is at point B, the battery is no longer in the circuit. So just like yesterday, what's the potential drop across here? And what's the potential drop across here? Okay, so delta VR will just be IR, and delta VL will be L dI over dt. And this is my source of external EMF, say 10 volts. Okay, so initial condition, connect what will happen? There will be a current that will start to flow in the circuit. That current resistance R. So the current across R will start to rise. Now, if L was not present, not in the circuit, the current through R will quickly get to E over R and will become stable. I shouldn't say across R, through R. Current through R. Now, however, in this case, L is present. Now, what is the effect that L is going to have in my circuit? What did we say? L, according to Lenz's law, will do what? So here, where was it? Right here. When you have an increasing I situation, what does the inductor do? It produces an induced EMF that opposes that change, right? Great. So, according to Lenz's law, the inductor will provide an induced EMF that will oppose the rise in the current. In other words, you can also say that it opposes the polarity of the battery EMF. It's almost like it's working against the battery. Now, what will happen to the current in the circuit? So now the current in the circuit will then depend on two factors. One, the constant EMF that the battery is giving, that we called E, and two, the variable EMF due to having the inductor in our circuit. Right? And they're both opposing each other in the charging case, right? So, which implies that the current in the circuit will always be less than the max current that is E over R, right? Because you always have EL that is opposing it. Now, after some time, what will happen? The current will increase less rapidly, which implies that the opposing EL will become proportionally smaller? Is that true? And this continues on, right? As current increases less and less and less rapidly, the opposing induced EMF will become proportionally small until it reaches a point after even more time, the induced EMF that we called EL becomes very, very small. And the current in the circuit approaches E over R. Note the word approaches. As long as there is an inductor in the system, it will never actually get to E over R, right? Because every time it tries to get there, there will be opposing EMF that's there. So I can put this in a box and I can say, initially, L behaves as a infinite resistor with I equals 0. Much later, L behaves as a resistor of 0 ohms and current becomes steady.